Let us turn our attention to three-dimensional force systems rather than just two-dimensional. After today, you will be able to solve 3D particle equilibrium problems. And the way you'll do that is by drawing a free body diagram and then applying three scalar equations for equilibrium based on a single vector equation. Now, normally if we were in class together in person, we'd go through this list and do all of these things. As usual, I want you to get the slides after we're done with the lecture. I want you to look through them, do your best to answer the questions, do your best to go through the example problems and understand the ones that are in the slides. And of course, I have other example problems for you as well in the course. So what applications would there be for a three-dimensional force problem? Well, we've got an electromagnet here that needs to stay in a particular plane for the most part, and it is connected to the hook via three chains, AC, AB, and AD. So how would we know whether or not this assembly is safe? How would we know if the electromagnet would take the load or would the chains break? How would you calculate the force in each of these three chains, since the chains are no longer in a single plane, rather they are in 3D space? Well, it's actually very similar to how we did it in two dimensions. It was just a slight variation on that theme. There are other applications. Here's an example of a shear leg derrick that is supported by a rope or a winch of some type. Maybe it's got, a cable supporting the upper level, and basically it's designed in order to lift up a certain amount of fish. Now, it can't lift just any weight. Eventually it would break. How would you determine the effect of changing the offset distance? Because the way this works is that winch pulls on the top point of those two legs and they pivot back to lift the fish. So as that offset distance changes, right now it's at 4 meters, but as that offset distance changes, how would you determine the amount of force in the legs of this derrick, the legs from A to B and B to C? Well, it's a three-dimensional problem because all of the forces here exist in 3D space. The weight from the fish obviously acts only in the Z direction, but the force from the cable, the winch I should say, apparently from the drawing lies in the YZ plane, whereas the legs have components in, of course, the Z, the Y, but also the X direction. So how would we calculate those forces? And the reason for calculating the forces, of course, is to make sure that we build these things out of materials and sizes of supports that can take the load. Well, it's just we extend the two-dimensional equations of equilibrium to 3 dimensions so that we have 3 equations. The vector equation is still identical to what we had in 2 dimensions. It is simply the sum of all the forces on the particle must be equal to 0. So this equation can be written in terms of its components, but now instead of just having 2 components, an X and a Y, now we also have Z. Now, one thing that often happens that might trip you up a little bit, usually when we're dealing with two-dimensional problems, the Y-axis is the vertical axis, and gravity will act along the Y-axis. Most times. Sometimes we'll rotate the coordinate system, but most times X is horizontal, Y is vertical. When we move to 3 dimensions, what happens most times is that the Z dimension or the Z direction becomes the vertical direction and gravity acts in the negative Z direction. So it's a little bit of something you have to remember when you move from 2D to 3D problems. But basically we just get one more equation that is along the Z-axis, in other words, in the direction of the K unit vector. And then all we have to do to solve problems is set up 3 scalar equations based on the 3 components of the vector equation. The sum of the forces acting on the particle in the X direction must balance, otherwise the particle will accelerate in the X direction. Same thing for the Y direction, same thing for the Z. So this yields 3 scalar equations of equilibrium, and of course I've got example problems to show you how to use these equations and solve 3-dimensional problems.